Okay, so welcome to the seminar today, and it's a great pleasure that Matteo is back on our channel, and he's going to tell us something about how to have Maxwell and Higgs at the boundary of AdS. Okay, over to you, Matteo.
All right, so thanks a lot for the invitation. Very nice always to be back here. At a certain point, I will also be back in person. So today I want to tell you a little story about how to introduce Maxwell and Higgs on the boundary of AdS, and I will clarify by that. Also, please feel free to interrupt me whenever you like with questions if something is not clear. So the talk today is based on this work that we did in the last couple of years. In collaboration with many people, most of them from Korea and China. And the last one is actually not a paper, it's just a conference proceeding where I summarize the content first two. So if you want just to go very quickly through the results, maybe that's the best way to start. So the question that I want to start with, it's actually related to the fundamental picture of holography. And the idea that holography is a correspondence between a gravitational bulk theory and the boundary QFT. And at least in a sense, this is quite imprecise because given a certain gravitational bulk action, that does not identify uniquely the boundary quantum field theory. And the ingredient that actually is missing, and it's fundamental, as we will see, is that the gravitational bulk action, or whatever it is, in whichever dimension you want to define it, must be supplemented with boundary conditions for all the bulk fields. And only in the moment where both the bulk action and all the boundary conditions for the bulk fields are specified, then this will correspond to a boundary quantum field theory, which is uniquely defined. So this is the precise statement, and of course it's nothing new, but it has a lot of relevance in terms of applications of the AdS correspondence. And in particular, I want to start with one example, which is a typical example which is used in the applications of the AdS to condensed matter. So what you see here on the top inside the red box, it's basically one of the simplest actions that we can write. It's just the Einstein-Hilbert action. So you can see here that you have your Ricci, your cosmological constant, and then we add to it a Maxwell term in the bulk, which is just in terms of a gauge field that I call A. And this action, it's basically the minimal action that allows to introduce temperature, charge, and magnetic fields in the boundary field theory. Now, given this action, there is a very simple solution, which is basically Reiser-Nostrom, which is a black hole solution in asymptotically AdS4 space. And this asymptotically solution has a certain form, which is not very relevant for this discussion. And then the gauge field as well is given by a certain profile in the bulk, where basically the time component is related to the charge, and what I call B here is just the magnetic fields on the boundary. Now, this is the action. But one thing which is maybe even more important than the action is that this gauge field has an expansion close to the AdS boundary, which in my notation is located at infinity, which is given in terms of two unknown coefficients, which, if you like, are just the integration constant of the second order differential equations that you solve in the bulk. And as a notation, usually we call the one that scales slower as the leading coefficients, which is indicated with a 0, and the other one is indicated as the subleading coefficients. Now, at this point, in order to uniquely identify what we're doing, we have to assume some boundary condition and to impose some boundary condition for these terms. And what we do usually, 90% of the time, is that we assume what is called standard quantization, which corresponds to impose Dirichlet boundary condition for these fields. So what we are doing is we are fixing the value of these fields at the boundary, which corresponds to Dirichlet. So in a way, we are fixing this A mu 0. And then running the holographic dictionary, what we are really doing at the boundary is we are taking our CFT action, which I indicated as S0, and is in general a function of all composite operator that we have that I label like capital phi. And we are deforming this CFT action with a deformation which takes the following structure, like A mu J mu, where A mu is a source for a current J mu, which is an operator of the CFT, given in terms of composite of the operator of the CFT. So this current is actually a composite current, which can be made off of various things, which in general, at least at low energy, we don't care. But the important thing is that you see here what we're really doing, and that's what is implemented in this generating functional, is that the theory does not have any dynamical gauge field, but rather the gauge field is an external source that we use to couple to the operator, the dynamical operator of the theory, which is a current. Now, for most of my talk, actually all of my talk, I will be interested in the low energy description of the systems. Now, if we do what I just outlined in the previous slides, what do we get on the quantum field theory side? On the quantum field theory side, we get a quantum field theory with a conserved U1 current in presence of an external gauge field. And if you just want to describe the low energy of this theory, what you get, the equation that you want to consider are these two equations. The first equation is just the conservation of the stress tensor that comes from the diffeomorphic invariant in the bulk. And the right-hand side is just the presence of possible sources that come from the gauge field. And the second equation is just the conservation of the current. And to make things more explicit, if I consider, for example, only the conservation of this current, what I do get, it's what is called charge diffusion, which is nothing else than what you see in this picture down on the right, is what happens when you throw colors in water. This charge diffuse, there is no ballistic propagation, but it's just spreading around in a diffuse way. So that's basically the physics of the boundary field theory, which corresponds to that gravitational descriptions if we follow this strategy. Now, the question that I... Yes, go ahead.
I mean, just by looking at those equations, it's not obvious to me why you get this diffusive behavior in the boundary. I mean,
yes, of course. So I didn't explain it at all. So what happened is that if you see the second equation, this equation is just around, which is exactly what you expect in a fluid. So if you have a charged fluid, the charge fluctuation.
Matteo, I just now, my network just decided to act up and I missed what you just said. So if you would not mind repeating, I would be very grateful.
Oh, okay. So I will repeat it. So the equation that you have here is the conservation of the current. And if you do the proper hydrodynamic description of this equation, what you get is you get that the fluctuation of the charge, which are the only degrees of freedom in the low energy description, just diffuse around. This is exactly what happened in the fluid. And this is telling you that the boundary, it's nothing else than a fluid with charge. So if you want, this is the same behavior that you find in, say, when you have particle of different type and you put a gradient and the particle will mix together in a diffusive way. And this U1, you can think about like particle number. The particle number is conserved, but you will have this diffusive behavior that will be driven by the gradient.
Okay. Okay, thanks.
Yeah, sorry to not be very precise. It's not really an important point. You will see what I want to say in a while. So now the question that I want to ask today, it's basically the following. Is this everything we can do, and are we happy with this? So of course, there are many systems where this is a good description in terms of applications. There are many systems which are fluid and for which this is a very good description. But there are also many systems, especially in condensed matter and in nuclear physics, where having a dynamical gauge fields, or if you want, having Coulomb interactions, it's extremely important. So some of them are mentioned here. Of course, electromagnetism. You don't have any electromagnetism without dynamical gauge fields. Also plasma physics, So plasma physics and all the physics related to ionized plasma, to neutron star, to nuclear physics, it necessitates the presence of dynamical gauge field, but also condensed matter system. So for example, plasmods, which are the reason why this nice glass of all this color necessitate gauge fields, dynamical, and of course superconductivity. So the reason why this magnet is levitating there, it's because there is a gauge field, dynamical gauge field over there. So if we want to understand or describe or learn more about these systems using holography, we need to learn how to put dynamical gauge fields in the holographic picture. And in the first part of this talk, what I will show is I will show you how to do that. Now, I want to tell you more precisely what is my motivation and why I arrived to this question. So the reason why I arrived to this question is the following. In the past year, there was a very interesting paper that tried to rewrite electromagnetism in terms of some novel global symmetries. So what is the point here? The point is that if you think about electromagnetism, the way we write electromagnetism is based on a gauge symmetry, on a U1 gauge symmetry. And if you think about it, this is good from one side, but from the other side, it's quite unsatisfactory because gauge symmetries are not physical, there's nothing there, while global symmetries are. So the question is, can we define electromagnetism just using global symmetries? And this gentleman showed that indeed one can do that at the cost of considering global symmetries which are generated by objects which are higher rank symmetries, in the sense that the corresponding conserved current, it's not a current with one index, but it's a current with two indices. And these objects are called higher form symmetries. And this is the way to do it. And what these people show is that in principle, you can forget completely about the field strength and the Maxwell equation, and you can describe completely electromagnetism only in terms of two equations, which are, one is again the conservation of the stress tensor, which is always there, is this equation here. But the second equation is actually the conservation of this higher form current. And what they show is that this formulation is completely equivalent to standard electromagnetism, but is actually convenient in many respects, especially when you want to study the limit of strong magnetic fields and when you want to do hydrodynamics, because hydrodynamics is based on real symmetries, and real symmetries are global symmetries. Now, after that, same people showed that if we now follow that logic and we build in holography a theory which is based on a two form, we get something very interesting. Now, let's look at the structure of this action here. So this action here is exactly the Maxwell action, but for an object with one additional index. So you see here, the field strength has now three indices, and the gauge field has two indices. So it's an antisymmetric two form. And of course, this action has an obvious and trivial gauge symmetry in the bulk, which is just shifting this B2 form to like B plus d lambda, where lambda now it's a vector. And if you do the standard holographic dictionary, what you find out here is that this system has a gauge symmetry in the bulk, which is this higher form symmetry. Hence, it has the same global symmetry in the boundary. And then accordingly to what these people are saying, this system should give you a boundary theory with dynamical gauge field, because it will give you Maxwell equations. And that's exactly what they proved. So what they prove is that when you look at the dynamics of the boundary description, what you find out is exactly what is called relativistic magnetohydrodynamics. So relativistic magnetohydrodynamics is a very fancy word to say a quantum field theory with dynamical gauge field. So you have dynamical electric field and dynamical magnetic fields, which are not present in the usual description. So if you follow the standard picture in holography, there's no electric field and there's no magnetic fields, which are dynamical. They're just external. And here, of course, the interest is towards, magnetohydrodynamic system. For example, there are many effects which are very interesting from the point of view of nuclear physics, like these alpha waves in the sun and these magnetosonic waves. And I will tell you more about this in the next slides. So they get this very funny, magnetohydrodynamics at the boundary. But then when I read the two paper,
sorry, can I ask a question? So is this mean that the usual Dirichlet condition, boundary condition itself gives you a dynamical gauge field or at the boundary, or
Yes,
what is
that's
it?
a good point. So the standard Dirichlet boundary condition for the standard gauge field in the bulk does not give you dynamical gauge field. Now,
Yes.
if you use this higher form and you put standard boundary condition, you find dynamical gauge field. And the question is, why? So,
Oh, okay.
yes, so that's
Yes.
exactly what I was going. So the question is, where is the trick? And why this question? Because if you think about the bulk and you go back a second, this theory, it's exactly equivalent to Maxwell action up to a notch dual. So you're not doing absolutely anything in the bulk. You just do a notch dual of this action and you get Maxwell action. So
Yes.
the question is, then how can it be that you get something so different at the boundary? And the second thing is, do we really need these things, or can we do it also with the gauge field? And is there another solution? And this is exactly what I want to tell you today. So let me first start back 1 second with field theory. So in field theory, let's go back to our generating functional. This is a generating functional in terms of an external metric, which for these talks I will not care about, and an external gauge field. Then what do we do usually in holography? What we do is we take variation of this generating functional with respect to the source, which is the gauge field, and we can find all the correlation function of the dynamical field, which is the current. So we can take, for example, we can get, for example, the 1-point function of the current, the 2-point function of the current, and if we are good enough, we can get the 3-point function, 4-point function, etc. And this, of course, relates to physical objects. Like, for example, the 2-point function of the current is what we call conductivity, etc., etc. Now, if we want to add a dynamical gauge field, what do? We take the action that we had, and we do two things. The first thing that we want to do is a Legendre transform, where we switch the degrees of freedom from the gauge field, which was external, to now a current, which is external. And then we add a kinetic term for that gauge field with a certain coupling, which in this case I call lambda. So when you do these two operations, so the Legendre transform plus adding the kinetic term, you can convince yourself immediately that now if you take the variation of this total action, what you get is exactly Maxwell equations. So this means that now the total action defined like the previous one plus the Legendre transform and the kinetic term are giving you exactly Maxwell equations. So this action now has a dynamical gauge field, and the dynamical gauge field follows standard electrodynamics rule. Now the question, and of course now if you do the aerodynamic description of these systems, now it's very different from before. Why it's very different from before? Because now, of course, the stress tensor conservation is always there, but now the stress tensor has two components. There is a component from matter, whatever it is, and a component from the electromagnetic fields, which of course take the standard form of the electromagnetic stress tensor. And then you have the conservation of the current, which is automatically imposed here. But on top of that, you have an additional dynamical equation, which is nothing else than Maxwell equations, which is the one here on the top left, on the bottom left. And of course, together with that, you have the Bianchi identity, which is just a consequence of the gauge structure.
Sorry, I have a confusion.
Yes.
So in this equation, this is the bulk conservation equation for the stress tensor, or is it the boundary conservation?
For the moment here, I'm not doing all this is field theory. There's no bulk or boundary. I'm just doing field theory.
Oh, okay.
So I'm starting this action here.
Yes.
It's defined in a 3-dimensional field theory, and I'm not doing any holography.
Okay, this is 3-dimensional field theory. Okay.
Yes, this is just basically, I start from a field theory where I have a current coupled to an external gauge field, and I want to introduce in the field theory a dynamical gauge field which follow Maxwell equations. And what I'm saying is that in order to do that, you need to add these terms here.
Sure. Yeah. Okay. Thank you. Yeah.
Yes. Now, if you do that, you get trivially these equations, which are the equation of magnetic hydrodynamics. And then, of course, the next question that you want to ask is how I do that in holography, right? So how I implement that in the bulk. And the main things, which is basically summarized visually in this picture, is that you need to play with boundary conditions. Now, this idea is definitely not new. And it's the idea that the possible boundary conditions that you can put in the bulk are much more general than Dirichlet. This was, introduced by Witten already a few years after the definition of the lograph of the AdS correspondence, and was basically defined in a very formal way by Maroff and Roth in a very nice paper. And let's make the example of the gauge field. So if you take the gauge field, as I said, there are two terms. One is the leading and one is the sub-leading. And then what this gentleman says is that the most general boundary condition that you can do is basically a linear combination of these two terms. These are integration constants that the equation of motion will not tell you what they are. And you can fix a generic combination. Now, if you set beta equals 0 in this language, you are fixing a mu 0, and you are fixing, therefore, the value of the gauge field of the boundary. These are standard Dirichlet. On the contrary, if you fix alpha to 0, you do what is called Neumann boundary condition. So you are not fixing the value, but you're fixing the derivative of the field. But in general, you can do mixed boundary condition. And the mixed boundary condition, the most general form, takes this structure. Now, why I'm telling you this? Because this will play a fundamental role. Now, the fact that mixed boundary conditions play a fundamental role was first realized, at least in terms of applied holography, in the context of superconductivity. And the first paper that did something related to that, and I will get back to this in a while, is, to my knowledge, this paper down here. And the reason is very simple. The reason is what we call an holographic superconductor. So the paper of Arnold, Herzog, and Horowitz, which is very famous, it's not a superconductor. It's actually a superfluid. And the question is, the immediate question that people realize very soon after, it's how can we make a real superconductor? And as you will see, some of the properties of a superconductor are very different from the property of the superfluid. For example, the standard picture that everybody showed that the magnet levitates, it happens only in the superconductor. In a superfluid, there's no magnet levitating whatsoever. Now, this was realized in the past, and then for many years, at least in the context of applied holography, was completely forgotten, until very recently, where people started to discuss plasmons. So plasmons are excitations, gapped excitation, that appear in polarizable matter, which can be derived very simply from Maxwell equations. And they are responsible for many important features in condensed matter system, and also for many nice features in arts. For example, this decoration that you see in the churches are basically related to plasmon physics. And now the breakthrough, in my opinion, related to what we were doing was actually given a few years ago in this nice paper here. And it goes back to our original question. So when I start basically thinking about this, I found this paper and I realized that somehow the answer to my question was already there. So if we go back to our doubt is that we know that Maxwell action with Dirichlet boundary condition give rise to external gauge field in the boundary. But then these people show that if you put actually a higher form, which is just a notch dual in the bulk, you get dynamical gauge field on the boundary. So then how can it be? And the answer is given very precisely in this paper.
Sorry, Matteo, that particular comment applies only to 5-dimensional bulks, right? Like if I had a 4-dimensional bulk or a 3-dimensional bulk, the Hodge dual of the 3 form is not a gauge field. I mean, it's not an FEM.
That's correct. That's correct. But you can still generalize this argument in general. So of course, it will not be a gauge field. It would be like, for example, either a scalar or a higher form or whatever. But this argument is always valid. Now, of course, if it's not a gauge field, you can ask yourself, what are you actually making dynamical at the boundary? That's a different question. But yeah, you're totally right. So what I will talk here about it's basically AdS5, but you can also do it in AdS4. But in AdS4, indeed, if you dualize it, you dualize a vector to a vector.
Yeah, okay.
It's not actually a higher form. You're correct. Now, this particular structure here, indeed, is for AdS5. And in AdS5, but the main message is that the Hodge dual, which looks like very innocent in the bulk, it's actually not so innocent. And the reason why it's not so innocent is that indeed the bulk picture is exactly the same. You're just doing an Hodge dual. You're not doing anything. But the boundary conditions are not preserved by the Hodge dual operation. So whenever you do the Hodge dual,
Can I ask? So is there a way you can get the standard boundary condition from the Hodge dual? I mean, is there, or is it
Yes.
not possible, or?
yeah. So what this paper show, I don't show the detail, but you can map exactly the boundary condition of the standard field and the boundary condition of the Hodge dual. So you can really see how to map one-to-one the two. That's what this paper does, actually. So you can do the exercise. You can say, okay, I start from a field in the bulk, I impose generic boundary condition, then I do the Hodge dual, and I see in terms of the Hodge dual field how these boundary conditions are mapped. That's what this paper does.
So there
And
is
you
some
can
kind of
do it-
duality of the boundary conditions, that what is Dirichlet becomes free, or.
Exactly,
and
exactly.
that's,
Yes. So basically, you are mixing the boundary condition. What is Dirichlet for the bulk gauge field, it's not Dirichlet for the Hodge dual field. And that's basically how these people, without realizing, make these things dynamical. Because in the bulk, you're not doing absolutely anything. But what they were doing, idly, they were taking the standard gauge field, but they were not applying Dirichlet. And what I want to show you now in a second is what they were actually doing. They were imposing mixed boundary condition. So in order to understand this point, let's go back 1 second. So now I'm talking about holography, and I have, for simplicity, I stay in 4 dimensions. So forget about higher form here. I'm in 4 dimensions. I have my Maxwell action. Now I know that if I don't do anything else, this Maxwell action will correspond to the boundary to a non-dynamical gauge field. And then I want to ask myself how I make it dynamical. Well, I make it dynamical exactly as I made it in the field theory. I add a boundary term. Note that now this is a boundary term. So this is a field theory term. It's not a bulk term, where I basically do the Legendre transform and I add the kinetic term. So if you want, I'm basically putting by hand that this field is dynamical. And so far you would say, well, you're just doing by hand. But the tricky thing is that if now you study this theory, what you realize is what you are actually doing is you are considering the original bulk theory with the form of boundary condition. So in order to do that, you just need to take the variation of the total action with respect to the boundary source. And of course, you will convince yourself immediately that the action that you are getting is the Maxwell equation, is this equation that I write here. But now if you look carefully at this Maxwell equation and you write it in terms of the bulk field, you realize that this equation is nothing else than mixed boundary condition for the field. Let me show you why. So you see this pi mu, which is actually the current is the subleading of the field. Okay, so you see it's basically the derivative is the field strength at the boundary. It's not the gauge field. So this is basically like a Neumann boundary condition. If I fix pi mu, I'm basically putting Neumann boundary condition. On the contrary, if I put so in a sense, these terms here, if I write it in terms of the bulk structure, it looks like exactly what Marov and Ross were writing. And here is basically the things made precise. So if you write this equation precise, the boundary condition that you get, so this equation gets rewritten in terms of this variable here. Now, what I call capital Z are basically gauge invariant variables in the bulk, which are more convenient to do computations. But the only important message here is that whatever stays with L means that is the leading, and whatever is F is the subleading. Now let's look at these things. So first, I don't want to put any source. Okay, so if I don't want to put any source, what I do here is I need to put this source to 0, because now these are the sources. And now let's look at this equation equals 0. So if you look at this equation equals 0, in absence of lambda, remember lambda is the coupling of the dynamical gauge field, then if you remove this and you set this to 0, this is just Dirichlet, right? So what are you telling? You are telling that, of course, if you eliminate the dynamical gauge field and you remove the kinetic term, you get Dirichlet boundary condition, and there is no dynamics for the gauge field. But now what you see is that if you add that, you see this equation. Setting this equation to 0 is exactly setting a combination of the leading and the subleading to be 0. So it's exactly a mixed boundary condition. where this corresponds to basically there would be Neumann if you just set this to 0 and this to Dirichlet. And the coefficient in the middle is the precise coefficient, which is determined by basically the coupling of the electromagnetic theory at the boundary. Okay? And this is basically what you get. So in other words, you can show that adding basically dynamical gauge field at the boundary, it's nothing else than considering exactly the same bulk theory, but imposing different boundary conditions. And again, to go back to the higher form business, which is the reason why I get to these ideas, the higher form in the bulk, so the Hodge dual, is exactly doing this. So ideally, if you do the computation, you realize that the boundary condition that you are putting for the Hodge dual are exactly this boundary condition. And that's why those people got dynamical gauge field using the Hodge dual.
This is very nice, but I have one question.
Yes.
So is there a way to capture the 5-dimensional Chern-Simons section in terms of the Hodge dual?
Yes, that's a good question. So let me see. So you can ask even a simpler question. How do you couple to matter? Because imagine you start from Maxwell and you couple to matter like a scalar. If you do the Hodge dual, how would you write that? So, and I think the answer to this question is related to something even older and simpler, which is what you are really doing here in the bulk. So this Hodge dual in the bulk, if you like, it's some kind of generalization of particle vortex duality. So then you have to be careful because the two languages might be convenient in one phase or in another, but in some of these phases, the realization of this could become very non-local. So I haven't thought in detail about the Chern-Simons or how to couple to matter, but I suspect that, of course, you cannot do that in an explicit way if you have coupling to matter or Chern-Simons terms or things like that. Like, for example, if you have in AdS 5, say A, F, F, how you do the Hodge dual? It will become highly non-local because A, now you cannot write it in terms of a local thing. So I agree. I don't know how to do that. I don't know if there is a good reason why, but that's a good question.
Yeah, but this is what you need, for example, to produce this anomalous terms in hydrodynamics, anomalous transport coefficients, right?
Yes, I agree. I agree. Indeed, if you would that's one of the reasons why I believe that using the language of the gauge field is more powerful. Because, for example, if now you want to do exactly what you want to do, which is actually what people are discussing, if you want to do chiral magnetohydrodynamics, meaning that now you have magnetohydrodynamics plus chiral anomaly, I have no idea how to do chiral magnetohydrodynamics in terms of this higher form, but in the bulk, but I think I know how to do it in terms of these gauge fields. It's also fair to say that I didn't follow that much this higher form, but there are recent papers where I think they claim they can do it also with the higher form. But the structure is pretty complicated. So I don't know enough about that. So my take, from my perspective, the gauge field language is much simpler because it's what we're used. So the only thing that you're really changing is the boundary condition. So if you want to do chiral MHD with what I just showed you, no problem. You add the Chern-Simons term in the bulk, you change the boundary condition for the gauge field, and you're done. In the higher form language, I don't know how to do that. It must be more complicated. Did I answer?
Yeah, thank you.
Yep. So then, okay, well, so this is the message, okay? So there is basically this way. And again, let me emphasize that we didn't discover this method. This method was there for ages, and somehow people, didn't pay too much attention. But it's a very well-known description. Now, what we want to understand is if this works, to which extent it works, and how can we use it. And so, well, then when you start doing these games, and I want just to tell you one thing which is curious because I didn't know it at the beginning, so I was like puzzled. So when you do the story, for example, one first thing that we discover is the following: is that now if you change the boundary condition, of course, the stress tensor definition changes because you are modifying the boundary theory. And what you find out is that if you do it in AdS 4, you find out that the trace of the stress tensor actually does not vanish. And at the beginning, I was like, how can it be? I mean, I'm doing some mistake. We have some mistake somewhere. But then I realized something that, of course, we were just rediscovering something which is very well known. So if you take Maxwell theory and you take it in dimensions which are different from 4, so you want to take, for example, 3 or 5, you will discover immediately that Maxwell theory is scale invariant, but it's not conformal invariant. That means that the trace of the stress tensor does not need to vanish. The trace of the stress tensor just needs to be equal to the divergence of a vector, which is called the virial current. And for the case of Maxwell, that result is exactly what we found out with holography. So basically, with this holographic model, we rederive immediately what these people derived using field theory. And it was kind of nice because for us, it was really immediate. You don't need to do absolutely anything. And for them, if you check what they do, it's quite complicated field theory analysis. So that was nice. It was like already a signature that we were doing the correct things and we were getting the correct results. And then what we wanted to do is the following. We wanted to understand if really this theory was doing what it was supposed to be. And in order to do that, we started from the low energy description. So we started comparing that theory with what is magnetohydrodynamics. Now, let me sketch very quickly, just on these slides, without giving too much detail, what our magnetohydrodynamics is built. And to be fair, this is the standard procedure where which basically every hydrodynamic theory is constructed. So the step one is you start from the equation of motion, which basically follow from the symmetry of the system. So in our case, these are the same equations that I showed you before. They're just coming from the conservation of energy, the conservation of momentum, and the dynamical Maxwell equations. Then what you do is you write constitutive relation, which means that you expand each of the field entering this equation in terms of a gradient expansion, in terms of derivative. So you start from equilibrium, and then you start adding derivative that basically describe out of equilibrium effects. And you do this in a series expansion. Then what do? You take this constitutive relation, you pull it back in the equation of motion, and the equation of motion will become a big matricial problem in terms of the degrees of freedom that you have. What are the degrees of freedom that you have? The degrees of freedom that you have are the fluctuations of the dynamical field or the conserved charge. So for example, you have the fluctuation of the temperature, you have the fluctuation of the velocity, or if you want the momentum. And in this case, because we have dynamical electric and magnetic fields, you also have the fluctuation of the electric field and the magnetic fields. Now, since we are doing it in AdS4, you can notice here that the magnetic field is actually not a vector. This is a simplification, which is just because we are considering the theory in two spatial dimensions. Now, after you do that, you can run your hydrodynamic computations, and what you find is a bunch of dispersion relation, which gives basically the energy of each mode as a function of the wave vector. Now, in the limit of zero density and zero magnetic fields, the things become quite simple because the gauge field decouples from the metric, from the stress tensor. So you get basically a sector, which is very common. It's just a standard sector of the fluid. And this is what you get. So you get sound, longitudinal sounds propagating fluids. That's nothing new. So this is sound. And this is just the diffusion of momentum. So this is just what we call shear diffusion, is what gives rise to shear viscosity. And that's the shear viscosity indeed. Nothing new. So, but we get additional stuff. And this is already where interesting things happen. So if you check at the modes, these are the bullets are the numerical modes extracted doing quasi-normal mode computation. And the line are actually the hydrodynamic formulas. Now, what you see is the following, is that there are sound waves. You can clearly see two propagating modes here. There is shear diffusion, which is this yellow mode here, only imaginary, purely imaginary. But on top of that, you have two modes. And these two modes, I will show you in the next slides, that are exactly electromagnetic waves and damped charge diffusion. So if you follow the hydrodynamic theory, this is what you get. Now, let me start from the right because it's less interesting. So the right terms, in absence of dynamical gauge field, you have to remove these. And what you get is just charge diffusion. It's exactly what I was mentioning at the beginning. This is the diffusion of charge in a charged fluid. Now, if you have dynamical gauge field, charge does not diffuse anymore, but actually relaxes around. And this is an effect which is very well known. It's just the effect of screening, which is now there because you are considering a medium with dynamical gauge fields, so with polarization. Now, this is more interesting. So what is this? So let's look at this. So if we look at this, let's kill this term for the moment. This is nothing else than the propagation of electromagnetic waves. This is a photon. Okay, and you can immediately see here the speed of light in the medium. Now, these terms here, it's more interesting. These terms here, it's again due to screening. And you can actually find this equation in all electrodynamic textbook. The difference is that in the electrodynamic textbook, usually we solve this equation in terms of real frequency and complex wave vector. And what this equation gives rise is what is called skin effect in electrodynamics. So the fact that electromagnetic waves decay inside a dielectric because of screening effects. And this is basically a first manifestation of the fact that in the boundary, not only you have a dynamical photon going around, but you also incorporate immediately the effect of polarizations. So the medium is really reacting to this gauge field, these external gauge fields. And of course, you can see immediately also one thing which is important, which is these effects, which are parameterized by this sigma divided epsilon E, where epsilon E is the electric susceptibility, basically. It's proportional to lambda. So remember what is lambda. Lambda is the coupling of my dynamical gauge field, and is exactly what makes the boundary condition mixed. So if I send this lambda to 0, you see this goes to 0, and all these effects vanishes, which is what we know, because you are just killing basically the dynamical gauge field, and you're going back to what you knew before. So, and these are the numbers.
Sorry, I am not familiar with this damped charge diffusion. So what is it, how can you understand it a little bit? Like
Yeah,
why
so
it,
imagine you have a system with particle conservation. Particle number is conserved. And you want to study basically what is the dynamics of these systems. The dynamics of this system is basically what is shown in this picture here. What happened is that these particle numbers will move. For example, if you have a gradient like here, you have more particle of one color from one side, more particle of the other color from one side. Let's imagine this as charge plus and this as charge minus, for example. Then what this system wants to do, wants basically to diffuse around and spread this particle around, but of course the number will be conserved. That's what happened, like, for example, in a standard charge fluid. In a charge fluid, charge will just diffuse around. There's no propagation of charge. It's basically
no,
like,
but I'm not familiar with why there's a damping term. This
okay.
so I know diffusion. Of course, yeah.
So yeah, the damping term comes from the polarization effects from screening. So the thing is that basically when now you have these polarization effects, these charges are screening, and the interaction between these, now these charges interact, there is Coulomb interaction between them. They're not just moving freely around. And these effects basically make this charge not to diffuse anymore, but basically to relax. And the reason why is that basically the charge inside the electric, the total charge will go to 0. So the final state must be a state where the total charge is 0. So you cannot have anything like that. And if you want, this is also related to the fact that you cannot have any electric field, right? So if you have a system with polarization, the electric field inside the electric is 0. So you cannot have charge moving around. Charge should just decay. This is basically the same thing. So actually what I'm saying in this slide is nothing new. It's just standard electrodynamics. It's just written in a different language, in the sense that usually in electrodynamics, we don't consider the frequency to be complex. We consider the wave vector to be complex, because we're thinking of, you know, a different setup. We're thinking of sending light of a certain frequency inside the medium. But these effects in optics, if you want, are very well known.
Okay.
Yeah. So, and this is basically the proof that, you know, this skin effect is actually there. So you see, the skin effects in this notation is realized in a different way. So if you send lambda to be very small, you see the blue is approaching a propagating photon. You see, it's basically becoming almost propagating. Now, if I make lambda very large, I make Coulomb interaction strong, I make polarization effects larger. And what I'm doing, I'm gapping away this photon. So this photon does not propagate anymore, but basically has a gap in wave vector. Now, if you solve this equation on the opposite way, what you will see is that it will decay in space. That's what basically is the skin effect. So this is basically the skin effect in an opposite fashion, if you want. And of course, you can see that the modes from holography and the hydrodynamics works very well. So they match pretty good. And then, of course, you can start doing more and more. And we did more and more. I will just now basically show you very briefly a bunch of slides convincing that these things is working. And of course, there are many physical things that one can study. For example, one of the things is that if you have dynamical magnetic fields, then in a plasma, sound is not just a pressure wave. So sound actually carry magnetic flux. And this new mode is called magnetosonic waves, is what replaces sound wave in the plasma. And you can see that basically if you do the complete structure, this is still a sound mode. You see it propagates just linearly with a certain attenuation constant. But if you study it in detail, you will see that this mode carry magnetic flux. And indeed, both the speeds and attenuation constant becomes strongly dependent on the magnetic fields. And here you can see some example. So this is a zero density and finite magnetic fields. You still see this propagating magnetosonic wave. And the speed now is very different from the speed of sound in a conformal fluid. So in a conformal fluid, the speed of sound is given by, it's basically fixed because it's given by the conformal symmetry forces the speed to be a constant. Here, it becomes a function of the magnetic fields. It's like a magnetosonic wave. And then, of course, you can do much more. You can put charge. And if you put charge, you go back to something that you know, again, very well, that in presence of charge, you are gapping away sound. This is what is called the plasma frequency. And again, this is a very well-known property of plasmas and metals that if you want to propagate light, you have to go to a frequency which is actually higher than the plasma frequency. And this is behind the many properties of system, for example, the fact that metals shine and many other things. And of course, you can get this plasma frequency with this mixed boundary condition. And again, you see that the plasma frequency is actually proportional to this lambda again, which comes from the mixed boundary condition. So this is again known because if you don't have Coulomb interaction, you don't have plasma frequency. There's no plasma at all. So again, this is an effect, if you want, of screening. And of course, the hydrodynamics becomes complicated. You can do the full analysis. It's not really what I want to focus today. And again, the hydrodynamics, or if you want the low energy description, because to be precise, this is not really hydrodynamics because you can see that all the modes are gapped, works pretty well. So in summary, what I want to show, you see, these are other examples. What I want to show in the first part, it's that using the Maxwell theory with mixed boundary condition, indeed makes the gauge field at the boundary dynamical, and one recovers completely the low energy structure of magnetodynamics. So in other way, with this, I want to basically convey a bunch of messages. The first message is that, as also Ayan was suggesting, these higher forms might be more convenient for certain things, but they're not necessary at all. So the fact that they worked is just because they were automatically for us implementing this mixed boundary condition, but they're not needed. And indeed, holography, it's more powerful than just considering a quantum field theory with external gauge field. And just by playing with boundary condition, you can do much more. Now, I will repeat it maybe at the end, but people started to play the same game with the metric. So you can actually have dynamical gravity at the boundary using the same kind of trick. But okay, it's not part of my talk. I will just mention it at the end as possible direction. Now, this was the first part. And of course, there are a huge amount of questions that one can ask, because what we wanted here to show is that it was basically a proof of concept. It works as it should. It works well. It gives exactly what it should give. And it's perfectly consistent with everything we know about magnetohydrodynamics and electromagnetism. Now, the question is, can we do more? So can we extend? Can we do more than effective field theory? Can we extend? Can we help effective field theory and hydrodynamics in a certain way? Or are there phenomenological questions in this plasma that holography can, for example, help? And it's relevant for many things. For example, there is a lot of interest recently in QCD and neutron star. In neutron star, it's a plasma. So the gauge fields are dynamical, and these effects are important. Now, in the second part of these talks, basically in the 10-15 minutes remaining, I will show you how, using the same idea, you can basically build a real superconductor, a real holographic superconductor. Now, again, let me start with some complaints. And the complaint is that, this paper is great, but the title is horrible. And the reason why the title is horrible is because that's not what the paper is about. This is not a superconductor. it's almost a superconductor, but it's a superfluid. And of course, you know, again, superconductor and superfluid can be quite different in certain aspects. Now, these are two aspects where, for example, a superconductor is very different from a superfluid. The first one are vortices. So vortices in a superconductors are totally different from vortices in a superfluid. And that's exactly the main reason why these people discovered this problem, because they wanted to study vortices. And they realized immediately that if you consider vortices in the original model, you are not considering vortices in a superconductor. The second thing, which is again this picture that everybody showed, is the Meissner effect. So the reason why this magnet levitates is because a superconductor repels magnetic lines, and this is called Meissner effect. And mathematically, this comes because the gauge field becomes massive via the Higgs mechanism. And this is possible only if you have a dynamical gauge field. Now, very quickly, difference between superfluid and superconductor. So superfluid are basically about frictional flow. Okay, there's nothing about flow of current without resistance. That's a property of superconductivity. So superfluid is a flow without friction, without viscosity. Superconductivity is a flow of current without resistance. And at the level of the excitation, they're extremely different, because a superfluid has a Goldstone mode, which basically is incorporated in what is called second sound, and comes, of course, from the fact that a superfluid is a system that spontaneously break 81 symmetry. A superconductor has no massless degrees of freedom, because, as you know, the Goldstone mode is eaten by the gauge field through the Higgs mechanism. So the dynamics is extremely different. There's no massless degrees of freedom anymore. Now, of course, we know how to describe the two systems from field theory. This is very quickly a sketch. I will just spend 2 seconds on this. So this is Gibbs-Landau effective field theory. Is the standard simplified picture for spontaneous symmetry breaking. We have this double, this Mexican add potential, and which can be described just by, you know, these two terms, this quadratic and this quartic. And here we describe this in terms of a phenomenological complex scalar field with an amplitude and the phase. And then what we do, we very phenomenologically, we put that at a certain point, this parameter change sign. If this parameter change sign, then there is a minimum, which is away from 0. And then if I sit on that minimum will break spontaneously the U1 symmetry, and I will have 2 modes. One mode is basically the mode that brings me up and down this potential. This is a massive mode. And you can see it why, because it has to bring me up of the potential, so I need energy to go up. And the mass of this mode is nothing else than the curvature of the potential here. But then there is another mode which is completely massless, it doesn't cost energy, and this is the mode that basically brings me around this Mexican knot, and this is the Goldstone mode. Now, so this is all very, very clean, very clear. And then you can do more. So you can study actually superfluid with hydrodynamics. And this is basically a little sketch of what you do. It's again very well known. And what we showed in a paper like few years ago is that if you actually consider this structure of superfluid hydrodynamics, you can match exactly the model by Arnold, Horowitz, and Herzog up to coefficient. So everything matched perfectly. That system is a superfluid, and is exactly a standard superfluid, nothing special. Now, if you want to do superconductor, what do you do? If you do Gibbs-Landau, what you want to do is basically, you want to add, of course, a gauge field, which is dynamical, and you want to make it covariant. So you want to make all derivatives covariant. And then you can realize very quickly, just with some simple computation, that if you do the same kind of analysis, you will discover immediately that the gauge field becomes massive. And this is nothing else than the Higgs mechanism, if you like. So there is no Goldstone at all. So the degrees of freedom of the Goldstone disappear. The gauge field becomes massive, and basically the equation that is satisfied is this equation where this is called basically the Gibbs-Landau parameter, which is just the mass, if you like, of this gauge field. Okay, and this mass controls many things. Controls, for example, the Meissner effect, the penetration of magnetic fields inside a superconductor. It's basically the responsible of this levitation stuff, etc., etc. Now, our question was very simple, okay, well, let's check. So if we take the original model of Arnold, Herzog, and Horowitz, which is just written here, this is just basically an abelian Higgs model in the bulk, and is super studied and very well known. But now we want to study basically this system in terms of modified boundary conditions. Now, let me say that there are many papers that already tried that, but nobody really studied the collective excitation. So our focus was really to show that the Higgs mechanism will appear through this modified boundary condition. Is there a question? No.
No, so sorry. No, it was fine.
Okay.
Not from.
Okay, so then the second application of this boundary condition, I want to show you that this makes a superconductor. Now, because I'm late in time, I will just go very quickly through what is the important thing, which is here. So what you see down there here are the excitation in the longitudinal channel. So if you do that in a superfluid, you will find a sound mode that propagates. So here, what you can see, look, for example, here. So this is the energy, if you want, or the real part of the frequency as a function of the wave vector. And you see that there's no excitation that propagates anymore. This excitation is actually gapped. You see here there is a gap. Okay, and the equation that basically describes this is this equation above here, where because of the superconductivity, you have two new parameters. One is the mass of this guy, and one is an additional damping. Now, if you remove these terms here and these terms here, you go back to superfluid. And you see that there is a propagating mode with velocity capital V and with attenuation constant gamma. Now, in order to show you that this is true, what we did here is to study in details the parameters that enter the dispersion relation by fitting the modes. So first of all, we fitted this parameter, and you can see two things, is this and this. So first of all, the different color are different value of the Coulomb strength. And you can see that these parameters are completely independent of the Coulomb interaction. So they're not the properties of the dynamical gauge field, they are a property of the superfluid. And that's exactly what you get. Not only that, their value is exactly the value that they get in the superfluid, in the same model. And this is basically what it was checked in this paper over here. Now, the other two parameters are actually the new one. So this and this are new parameters. You see they depend a lot on the lambda. And what you see actually is that if you send lambda to 0, this is basically, you see where lambda is becoming small with red, this parameter becomes smaller and smaller. If you set lambda to 0, you will find that this parameter is 0 and this also is 0. Okay, so these are two new effects that comes because you have dynamical gauge field, and what the most important effect is that they give a mass. So this mass is basically what, as we will see, the Higgs mechanism, if you like. And this is basically another way to see that. You see that at low temperature, you see that the real part of a mode is clearly massive. So there is a mode that becomes massive, this red mode. And it's very tempting to say that this mode is basically the Higgs mode, if you want. Now, to be fair, something similar is seen in the holographic superfluid, but the origin is completely different. So in the superfluid, in this paper here, they see also that at low temperature, there is a kind of massive mode. But this mode, as you can see here, is this mode, this blue mode here. And basically, what you see is that this mode here comes, and you see here where it comes, is this mode here, and then this mode here. It's a completely non-hydrodynamic mode. So it has nothing to do with the superfluid of the superconductor. It's just a mode that is non-hydrodynamics that for certain reason, at very low temperature, goes up and looks like a massive mode, but it has absolutely no feature which relate them to the Higgs mode. On the contrary, our AdS. And yeah, so this is maybe the clearest picture. So this is the dispersion relation of this Higgs mode at low temperature. And you can clearly see that this Higgs mode is a massive mode with a certain gap, and that the gap actually grows towards low temperature. And the imaginary part of this mode is actually constant. And so this is indeed what you expect from Gisborne-Landau. So if you do Gisborne-Landau, the equation that you expect for this mode is this equation here. So what you see here, you see that there is a mass. This is nothing else than the Higgs mass, if you want, or the Higgs mechanism. And indeed, this object here is proportional to basically the lambda, if you want, the coupling. And then there is also a damping. And if you see the structure that you get from Gisborne-Landau is that there is a crossover between a mode which is purely real, which is basically when this guy is much larger than the attenuation, and a region where actually the attenuation wins, and this mode is purely imaginary. So this is what Gisborne and Dow tell you for a superconductor, and that's exactly what we see here. So here you can see the crossover between omega h and gamma in the real data, and you see that going to low temperature, dissipation becomes smaller, and the real part dominates, and therefore at low temperature, you will see that basically there is a massive mode which is undertapped, which is exactly the Higgs mode. Now you can, there is one thing which is important, which is usually in superconductor, the mass of the Higgs mode is related to the superconducting gap. So this is a result in BCS theory, in the most famous theory for superconductivity. And this superconducting gap can be obtained from the conductivity. So in a superconducting state, the conductivity is capped, and it has basically this structure at low temperature, and this is true also in holography. So by fitting the conductivity, you can extract this gap, and this gap is nothing else than basically the condensate, if you want. It relates to the condensate. And so what we find here is that the Higgs mass that we find divided 2 delta, which is this gap, it's actually much, much smaller than 1. So if this was a BCS superconductor, it should follow this formula here. So this is a result which is extracted from weakly coupled BCS theory. Now, in our result, notice also that we didn't go exactly at 0 temperature because of numerical reasons, and also because we are doing the probe limit, so we're not that confident about 0 temperature. But at the lowest temperature that we can trust, you see clearly that this is very far from 1. And now there is the question, if this is really another signature that actually this superconductor that comes from holography is not a BCS superconductor at all. It's something like different from that, and maybe a strongly coupled, type of superconductivity. So let me go to the conclusion. So the second part, I show you that indeed by combining the standard holographic superfluid model and the mixed boundary condition, you obtain an holographic superconductor, a real holographic superconductor, where you are legitimately showing this picture. So now this picture corresponds exactly to the system that you are actually considering. And this is again another proof that these mixed boundary conditions are doing what you are expecting them to do. And let me finish with.
Can I ask something? In this story of this holographic superconductivity, what happens if you have this more general vector scalar theory, and this kind of in the extremal limit you get this non-trivial horizons. I think there was this paper by long back by Horowitz and somebody who said that the holographic superconductors can have many different types of ground states, and
Yes.
so there are different kinds of near horizon geometries and different kind of near horizon behavior one can get. So when you take the finite temperature or near extremal limit, don't you see any kind of interesting differences between these cases? Or?
Yes. So I cannot answer that question yet, because in this paper we just work in the probe limit. So I'm not allowed to go to 0 temperature. In order to study that story,
you're only working in the probe limit. I see. Okay.
We are right now doing back reaction. When we do back reaction, we can answer that question if the ground state is Lifshitz, AdS2, AdS4, or whatever. And I'm not so sure, but I think that it might play a role. I mean, it's not obvious to me that the structure of the ground state should be the same. Yeah, but so far I cannot answer that question, because you need to go to.
Yeah, so putting a small temperature could give also some radically different kind of behaviors, right? Which is.
Yeah, I mean, small temperature. The problem is that I'm literally working the probe limit, so I don't trust my computation even at low temperature, because the condensate becomes very big. And then
so whatever you're describing should be true in a very high temperature limit in a way.
Yes. So close to the phase transition
is much larger than the condensate.
Yes, exactly. So there I'm safe. Of course, I can kind of extrapolate my results down, but they're not reliable, so I don't have control. Yeah.
Okay, thanks.
But that's an interesting question. Actually, there is also related to this question is how much of, for example, how this number is it's really stable under back reaction or not, because we are going quite a low temperature. And you can see here, so in this plot here, you can see that it's kind of saturating at low temperature. But of course, we didn't extract this value because I don't know exactly. Here you are already, T over Tc 0.2. This is already quite low for the probe limits. So down here, I don't know how to trust it. It might be that, we just follow like this, but it might be that some big changes will happen here. So I'm not making any final statement about what happened here. That's basically the safe way to do it. Let me finish with some generic conclusion. So what basically, as a general message I want to convey is that, if you want to play with gauge symmetries, and not necessarily only U1 gauge symmetry, you can think about gravity, you can think about other possible, non-abelian interactions or whatever. Now we know very clearly how to basically make this dynamical gauge field at the boundary. And then this could be relevant for many things. You can think about, for example, QCD. In QCD, if you want to have gluons, you need to have gluonic interaction. You need to have QCD. And all the models of holographic QCD do not have dynamical gluons at the boundary. So in principle, for example, if you want to do that, that's the recipe. And then there could be many questions which can come from many different fields, condensed matter, plasma physics, QCD, etc., and even cosmology. For example, let me mention again, there are at least 3 recent papers which are very nice that show that you can do the same mixed boundary condition for the metric, and you actually get dynamical gravity at the boundary. So it's fun in a way, because many times when you start learning holography, you say, oh, holography is a correspondence between a theory with no gravity and a theory with gravity. Wrong. It's not true. This depends on the boundary condition that you're putting. If you put mixed boundary condition, you can easily have dynamical gravity at the boundary. And now what you can do with that, that's a different question, but that's definitely doable. And then there are also, of course, more fundamental questions which are related to how the symmetries in holography are realized at the boundary. And especially how gauge symmetries are realized in the boundary. And these, of course, can have more fundamental relations with these higher form symmetries and other aspects of holography, which goes beyond applying to some condensed matter systems or whatever you like. And with this, I think I will just finish here. And thanks a lot. And I'm happy to take more questions.
Thanks, Matteo, for this great talk. And indeed, it's time for questions. Let's have questions.
Sorry, I just have one question. So once we turn on dynamical gauge fields in the boundary, I can ask for Ohm's law, right? So how would we compute resistance?
Yes, that's a good question. So usually, you see, what you do usually when you have an external gauge field, you compute the conductivity, right? So you compute the conductivity by doing basically taking the electric field as a source and computing the current. Now, if you do this kind of dynamical thing, what you are computing, you don't compute the correlator of the current, you are actually computing the response function of the gauge field. So in this language, the conductivity comes from the dielectric function, if you want. And this also relates to the higher form symmetry language. In the higher form symmetry language that I showed you before, what the transport coefficient that you actually find, it's not the conductivity, but are the resistivities, because they're actually the inverse. So I don't think there is much studies in this direction, but definitely both using the higher form or this mixed boundary condition, you should be able to assess directly the resistivity. And it's an interesting question if you can get more, more physical features than the standard conductivity. Because you see, the concept of conductivity in presence of Coulomb interaction is tricky. Because of course now you have loop of photons that can renormalize. Renormalize. Now basically this is like what in condensed matter is called random phase approximation. You resum the loops and you get basically the geometric series. And that I think is an interesting question that can be approached with this setup and also with the higher form. So yeah, I don't have a clear answer, but it's definitely something that I believe these frameworks can do.
And another question was, have you any thoughts about how to compute the roton gap in the superfluid?
Well, that's a good question. So, well, first of all, I'm not so sure even that there is a roton. So, in principle, one has to compute the dispersion relation of the sound mode and see if there is a roton. It's not obvious to me at all that these holographic superfluid models have a roton. It's an interesting question, and it's also related to something that some people are studying about the Landau instability. So as you know, usually people believe that in superfluid, the Landau instability is given by basically when the roton, so the slope, when the velocity gets the roton. And it's not obvious at all to me. I have to say I didn't think about it, but that's definitely a question that it's interesting. So I don't know, first of all, if there is a roton. So yeah.
Thank you.
Welcome.
Matteo, has anybody studied this holographic superconductor in presence of some Chern-Simons in AdS5?
You mean with the real superconductors?
Yeah, the real superconductor. Yeah.
Not that I know. So most of the studies are actually for vortices, because people immediately realize that if you want to consider vortices driven by magnetic fields like a real superconductor, you need this boundary condition. So actually, the only people that consider this mixed boundary condition in the past are people studying vortices and dynamics of vortices, like for this Kibble-Zureg or vortex lattice, Abrikosov lattices, and all these things. I'm not aware of any study where they put like Chern-Simons to do some anomalous, like you can basically do some kind of chiral superconductivity or something like that. I have no idea if anybody did that. I don't think so. And again,
You actually do something more fundamental than just chiral superconductivity about what condenses. For example, you can have something charged under some, say, the magnetic thing condense, for example, dion kind of condensation, not the
yeah, I see what you're saying.
Monopole, magnetic monopole condensation, for example, instead of condensation of the charged object.
Yeah, well, the first thing that is not
so
obvious is that at least the standard theory that we have, there's no monopole. There's no magnetic monopole. So you need to learn how.
True.
You need first to learn how to put a magnetic monopole and then to condense it. But yeah, I think there are many questions that one can explore with this framework. I mean, yeah, I didn't think about condensation of monopoles or more things like that, but definitely can be done.
I see.
And again, you're right. Like your comment before, I think if you have a Chern-Simons term like that, I'm not sure how you can do a notch dual. I mean, it will become highly non-local because how you watch dualize the gauge field. I don't know. Maybe there is a more complicated way, but I don't see it clearly.
Yeah. Okay, so let's see if there are more questions. Okay, then if not, so happy holidays for tomorrow. We have a holiday tomorrow, actually. And and see you again. It was great to see you again, and hopefully we will we'll see you again soon.
Hope so. Okay. Thanks a lot for the invitation. Have a happy holiday then.
Okay. Ciao. Bye.
Bye-bye. Bye-bye.